Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. In the last lecture, we had looked or we had derived an expression for the approximate bit error rate in a wireless communication system with L receive antennas, and we said that therefore the approximate bit error rate, as you can see here, is 2L minus 1 choose L or 2L minus 1 CL 1 over 2 SNR raised to the power of L. This is the expression for the approximate bit error rate in a wireless communication system with L receive antenna elements or with receive diversity. Now today let us do some examples to understand this better. So let us do some examples to understand this thing. For example, let us, using the high SNR approximation, using the high SNR approximation for the bit error rate, find the BER or bit error rate for L equal to 2 antennas at SNR at or dB SNR equals 20 dB. So we are considering this example of finding the bit error rate in a wireless communication system with L equal to 2 antennas at SNR is equal to 20 dB. And therefore, since we are given that SNR is equal to 20 dB, that is SNR dB equals 20 dB, that implies that log 10 SNR equals 20 implies log 10 of SNR equals 2 implies the SNR equals 10 square equals 100. So the 20 dB SNR, as we already seen many times previously, means the actual SNR value is 100. And now our expression for approximate bit error rate with that is rather approximate bit error rate. Approximate bit error rate with L antennas, we had seen that this is equal to 2L minus 1 choose L times 1 over 2 twice SNR raised to the power of L, but we are given L is equal to 2 receive antennas. Therefore, the bit error rate equals twice into 2 minus 1, that is 3 choose 2 times 1 over 2 SNR raised to the power of 2, which is equal to 3 divided by 4 1 over SNR square. And now we have already derived that SNR is equal to 20 dB SNR means SNR is equal to 100. Therefore, bit error rate equals 3 by 4 1 by SNR square, but we are given that SNR is equal to 100. Therefore, this implies that bit error rate equals 3 by 4 times 1 by 100 square, which is equal to 0.75 times 10 to the power of minus 4, which is basically equal to 7.5 times 10 to the power of minus 5. So, we have calculated the approximate bit error rate for L equal to 2 antennas in this system at SNR equal to 20 dB, and we have found that the approximate bit error rate is 7.5 times 10 to the power of minus 5, which is very close. This is very close to the exact value. Remember, the exact value we have derived before, very close to exact value, and we had derived the exact value previously. The exact value was 7.2564 into 10 to the power of minus 5. So, this is very close to the exact. So, the approximate bit error rate is 7.5 into 10 to the power of minus 5, which is very close to the exact value 7.2564 into 10 to the power of minus 5 that we had derived previously. Alright. So, this is how we can calculate the approximate bit error rate at a given SNR in a system with L equal to 2 receive antennas. Now, let us do another example, the familiar example which we also done previously for the wireless system with a single antenna. That is another example. Which is basically using the formula for approximate bit error rate. Using our formula for approximate bit error rate, calculate the SNR required to achieve bit error rate equals 10 to the power of minus 6 in a wireless system with L equal to 2 antennas. So, in this example what we want to do is we are asking the question the other way around, that is, given a bit error rate which is 10 power minus 6, what is the SNR in dB required to achieve this bit error rate 10 power minus 6 in a wireless communication system with L equal to 2 receive antennas, alright. And therefore, again we can solve this question similarly. For L equal to 2, our bit error rate equals 3 by 4 times 1 by SNR square, that is for L equal to 2 with through antennas the bit error rate is 3 by 4 times 1 over SNR square. This is the approximate expression for the approximate bit error rate. And now we want to find for the given bit error rate, that is 10 to the power of, for the given bit error rate, that is 10 to the power of 6, what is the required SNR. So, I have 10 to the power of minus 6 equals 3 by 4 1 over SNR square, which means SNR square equals 3 by 4 times 10 to the power of plus 6 rather, which means SNR equals, we have SNR equals 0.75 into 10 to the power of 6 square root, that is under root of 0.75 into 10 to the power of 6, which is basically equal to 866.0254. So, the required SNR to achieve a bit error rate of 10 power minus 6 in a system, wireless system with L equal to 2 antennas is 866.0254. Now we want to convert this into dB, therefore the dB SNR is 10 log 10 SNR equals 10 log 10 of 866.0254, which is basically equal to 29.37 dB. So, the SNR in dB required to achieve bit error rate of 10 to the power of minus 6 with L equal to 2 antenna. So, this is the SNR required for BER equals 10 to the power of minus 6 with L equal to 2 antennas. The bit error rate required, the SNR required is 29.37 dB to achieve a bit error rate of 10 power minus 6 with L equal to 2 antennas. Now, if you notice, you will notice something very interesting. Let us go back and see these SNR required to achieve the bit error rate 10 power minus 6. Recall that for an AWGN channel, for a simple AWGN or digital communication system or our wireline communication system, let me write that clearly, or our wireline system for bit error rate, for a similar bit error rate equals 10 power minus 6, SNR is 14.19 dB. So, this is the SNR for our wireline or AWGN channel. That is for a simple, so for a conventional wireline channel, not a wireless system, that is which can be modeled as a simple AWGN channel. We saw that the SNR required to achieve bit error rate of 10 power minus 6 is 14.19 dB in the AWGN channel. And for the wireless system with a single receive antenna, for a wireless system, on the other hand, for a wireless system with L is equal to with L equal to 1 antenna across a fading channel, that is our relay fading channel, across our relay fading channel, we see that the SNR required for bit error rate SNR equals 56.98 dB, that is approximately 57, that is approximately 57 dB. So, we had seen that in a wireless communication system with a single antenna, that is L equal to 1 antenna, the SNR required is huge, it is 57, approximately 57 dB. So, in an AWGN channel, we have an SNR which is 14.19 dB, approximately 14 dB. And as we go from a wireline to a wireless communication system, this required SNR for bit error rate, for the same bit error rate 10 power minus 6 increases enormously to 57 dB, that is a huge amount of transmit power is required to achieve a similar bit error rate. And now when we go back, now what we are seeing in this wireless communication system with L equal to 2 antennas, this SNR dB that is required, the dB SNR has again come down, it has come down slightly, it has come down to 30 dB. So for with L equal to 2 antennas, for L equal to 2 antennas, so when number of antennas, the number of antennas increases from L equal to 1. So, as the number of antennas increases from L equal to 1 to L equal to 2, SNR required decreases from 57 dB to 29.37 dB. So, what we are seeing is that as the number of antennas is increased from L equal to 1 to L equal to 2, the SNR required to achieve the same bit error rate, that is 10 power minus 6, has decreased from approximately 57 dB to 29.37 dB, which means for a same noise power, the required transmit power to achieve this bit error rate of 10 power minus 6 has decreased as, that is for same noise power, required transmit power decreases, required transmit power P has decreased by 57 minus 29.37 equals 27.63 dB. That is, for the same noise power, the transmit power required to achieve a bit error rate of 10 power minus 6 has decreased from 57 dB to 29.37 dB. Therefore, the net decrease in the required transmit power is 57 minus 29.37, that is 27.63 dB, or we have a savings, a net savings of 27.63 dB of transmit power. That is 27.63 dB lower transmit power is required to achieve the same bit error rate 10 power minus 6 in a system with L equal to 2 receive antennas. Therefore, increasing the number of receive antennas has led to a significant decrease in the bit error rate, or for the same bit error rate, to achieve the same bit error rate, the SNR required is decreasing significantly as the number of receive antennas is increasing, and this is the key property and this is the key benefit or advantage that we derive by using the principle of diversity. So, this decrease in the bit error rate or this decrease in the required SNR to achieve the same bit error rate is arising because of the principle of diversity. So, this is the one of the main benefits of diversity. So, the increasing number of antennas leads to a significant saving or leads to a significant decrease in bit error rate, and this is the advantage. This is the advantage or benefit. Remember, we talked about diversity. This is the fundamental principle of diversity, This is arising because of diversity, and we will explore this. We will explore this diversity even more in subsequent modules. And just to wrap up this module, this diversity or this principle of diversity is an important aspect of wireless communication systems. As we have seen, since exploiting diversity, one can significantly improve the reliability by decreasing the bit rate of wireless communication, and this principle of diversity is used in all 3G and 4G wireless communication systems such as, so diversity is used in several (3G/4G) systems such as, for instance, WCDMA, that is wideband code division for multiple access. It is used in HSDPA, high speed downlink packet access. It is used in LTE, long term evolution, and it is used in the WiMAX standard. As we have seen, these two are 3G standards and these two are 4G standards. So, diversity is a key aspect, is a key principle that is exploited in 3G and 4G wireless standards to significantly reduce the bit rate of wireless communication and thereby significantly improve the reliability of wireless communication system. And this arises, one of the ways to exploit diversity, as we have seen, is through receive diversity, which is basically done by increasing the number of antennas at the receiver. All right. So, let us conclude this module here, and we will explore other aspects of diversity in the subsequent modules. Thank you.